Hello everyone. Hope you're all doing well. Today we are kind of wrapping up the chapter. We are talking again about inverse trig functions. Talked about that a long time ago now, sort of at the beginning of our chapter 12, and we're finishing with the same idea. So let's review what we know about inverse trig right now. So what exactly is inverse trigonometry? Well, we have written inverse trig as our sign, for example, to the negative first almost is our notation we use, this little to the negative first, which we read as inverse sine of x is equal to theta. So that tells us that our input in a function like this is some ratio of side lengths. For example, for sine, or for the inverse of sine, that would be our opposite over our hypotenuse, opposite of the angle over the hypotenuse for the angle. Okay, the output though is going to be some angle measure, and that's either going to be in radians or in degrees. So one thing we maybe brushed over a little bit towards the beginning of the year was another way of writing inverse sine, or another way of writing inverse trig. So we're going to be using that a little bit more today. This arc sine is how we read this, is another way of representing inverse of sine. You'll see it as arc sine. You might have noticed actually on your calculators, especially if you're using a smartphone, for example, you'll see a sign instead of inverse sine written like this. Those are the same things. So of course our input is still the same. It's still going to be some ratio of side lengths, and our output is still going to be some angle measure. So we'll also have arc cosine, that's the same thing as inverse of cosine, and arc tangent, which is the same thing as inverse of tangent. Okay, so we're actually going to look at how we might be able to do these problems, believe it or not, without a calculator, which means we'll likely be using our unit circle. So for these homework problems, having a copy of that unit circle handy, one that perhaps you have practiced filling in, that would be really excellent. So to an example here. We are asked to find the value of arc sine. Remember, that's the same thing as inverse of sine of square root of 2 over 2. We want to write our answer, which will be an angle measure, in degrees and radians. We're going to be doing both. Okay, let's talk about some hints. First of all, we'll definitely want to be remembering or looking at the unit circle. And it's important to remember that our xy coordinates for each of those angles on the unit circle represent the cosine of that angle for the x coordinate and the sine of that angle for the y coordinate. So we'll definitely be looking at those coordinates for problems like this. Now we also, and here's our unit circle, we'll use that. We also want to maybe translate the question. It says to find the value of arc sine of root 2 over 2. That's kind of the same thing as asking what angles, notice plural there, have a sine equal to root 2 over 2. Another way I kind of translate that is what values of theta make this equation, sine of theta equals root 2 over 2, what values of theta make that equation true? Okay, let's look at our unit circle. We're looking for that root 2 over 2. But specifically for the sine of our angle. So specifically in the y coordinate position. So let's examine there. Okay, so 30 degrees is out. I don't see any root 2 over 2, but 45 degrees, I've got my root 2 over 2 there. So that's going to be one of my answers, 45 degrees or pi over 4 radians. Now let's see, I'm looking at all these y coordinates. I see another where we have root 2 over 2 as our y coordinate. So 3 pi over 4 or 135 degrees. That will be one of our answers. Now let's see if we keep looking. Well, I see a negative root 2 over 2, but negative root 2 over 2 is not the same thing as positive root 2 over 2. Those are different numbers, just like 1 is different from negative 1. So that's not an answer. And then I also see another negative root 2 over 2 there. That is also not an answer. So I do have two answers here. I've got in radians pi over 4 and 3 pi over 4, or in degrees 45 degrees and 135 degrees. Okay, so it seems like we've answered the question. We've solved this problem. But maybe not quite. So there's our angles that we've decided. Those are possible answers. But I want us to think about these as our terminals of those two possible answers. What about all of our various coterminal angles to these two angles? So for example, if I were to actually loop around a full rotation or full revolution around and still have the same terminal as 45 degrees, what would I be looking at? Something like this is what I'm talking about. So that would be 360 degrees plus 45, or let's see, what would that be? 405 degrees. So that tells me actually 405 degrees also has a sign of root 2 over 2. So it's also an answer. Well, okay, what then about if I loop around twice? What if I were to go, this is kind of a challenge to draw sometimes. Maybe I'll use this bright blue. I loop once and I loop twice and still have that same terminal. So it would be 360 plus another 360 plus another 45. Well, that angle measure, again, it's the same terminal, will also have the y-coordinate of root 2 over 2, which tells us the sine of that angle is root 2 over 2. So both of these angles, 405, we looked at that one first, that's 360 plus 45. The sine of that angle is also root 2 over 2. The sine of 765, 360 plus 360 plus 45, well, that's also root 2 over 2. Maybe another way to write that angle would be 2 times 360 plus 45. So I've only represented a couple of coterminal angles to just my 45 degree terminal side there. But I could also do the same thing with my other terminal, with my 135 terminal here. So there's actually, if we loop around and around and around, infinitely many angles that have the sign of root 2 over 2, or infinitely many answers to this particular problem. That doesn't mean we just say infinitely many solutions is our answer. We are specific about what our answers are. So to represent all of our possible angles that have a sine of root 2 over 2, or the answers to our arc sine of root 2 over 2, we're going to write 45 degrees plus 360 times k. K is going to represent how many times I'm doing a full rotation around my axes, or a full revolution. So those would represent all of my coterminal angles to 45 degrees. So we also want to say the same thing for 135 degrees. 135 plus 360 times k. So that represents all of the coterminal angles that have the same terminal as 135. Now in radians, the same idea, except we don't say 360 degrees for a full revolution. We say 2 pi radians. So let's take those radian measures, pi over 4 and 3 pi over 4, and add a full rotation. So pi over 4, that's again 45 degrees, plus a full rotation, but maybe like 12 full rotations. So pi over 4 plus 2 pi times k, where k could be any whole number. We also have 3 pi over 4, that's the radian version of 135 degrees, plus, again, full rotations. So our k represents some integer. Remember, that's a whole number, but it could be positive or negative. So we're also representing all of our negative coterminal angles here. Whole number, positive or negative. So k is some integer that essentially represents how many revolutions my angle is making. So it represents all possible coterminal angles. We would just have to pick a k. We could pick 0 for k. We could pick 25 for k, negative 40 for k. Those would all have a sign of root 2 over 2. So ultimately, the answer to this example is 45 plus 360k, etc. All four of those represent our answer. Okay, let's look at another one. This time we are finding the value of the inverse sine. Okay, we're not using arc sine this time, means the same thing. Inverse sine of -1. And again, we'll want to represent the angle measure in both degrees and radians. So in this case, I'm just going to sketch out my unit circle. And since again we're working with sine, I am looking for the y values that are equal to -1. So there's really only 4 interesting spots here that have a 1 even in the coordinates whatsoever. So remember, along our axes, we have here 1, 0. That's 0 degrees or 360 degrees or 2 pi radians. We have 0, 1 up here at 90 degrees or pi over 2. We now have -1, 0 for 180 degrees or pi radians. And then we have 0, -1 for, we could call this 270 degrees or 3 pi over 4, or excuse me, 3 pi over 2 radians. So we should hear like a little ding, ding, ding. That's what we're looking for right here, because this is the only coordinate, the only place on my unit circle where I have the y value equal to -1. Remember, the sine is equal to our y value. So this is our important spot. So again, in degrees, that's 270 degrees. And in radians, that's 3 pi over 2. Now we could also talk about the negative coterminal angles and all of the other coterminal angles. So for example, let's give ourselves a little terminal side here. Our regular angle, let's say 270 degrees, that just looks like this. Doesn't complete a full revolution around our circle. That's also 3 pi over 2. Now we could also, though, go around once and then some. So that would be 207 degrees, but plus a full rotation, or 360. And we could do that any number of times. We could loop around and around and around and around and around. And if we have the same terminal there, right along that, again, this vertical side that intersects our unit circle, that coordinate, 0, -1, then all of those various angles will have a sign of -1. That's what we're asked to determine. So we will add on to this 270 degrees plus 360k. Okay, that represents all of our possible coterminal angles, including the -1, I should say. Because if k is equal to -1, well, it's actually going not even a full rotation. It'll just be that -90 degrees right there. Now we also have to write the same idea, but for radians. So a full rotation in radians is, of course, 2 pi. So we'll say 2 pi k. Again, k representing how many times our angle is looping around. And that's our answer. This one's a little bit easier just because we don't have multiple spots on our unit circle that have the same sine value there. We just have the 1. Okay, let's make things a little bit more challenging. Okay, Find the value of sine of inverse cosine of root 3 over 2. This is a composition function. Dun, 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 right? So this is almost the exact same thing as if we were to say f of g of root 3 over 2. Except here we're saying f of x is equal to sine of x, and g of x is equal to the inverse cosine of x. We've just written our functions actually fully out here. So just like when we did composition functions a couple chapters ago, we want to evaluate the inside here first. So let's focus on what exactly is the inverse cosine of root 3 over 2. So let's pull up that unit circle again. Now we're talking about the cosine, so we're looking for x values or x coordinates that are equal to positive root 3 over 2. So where does that happen exactly? Well, let's see. I see 1 right off the bat. Here's an x value where I've got root 3 over 2. Okay, that's a y value. That one doesn't count. That is also a y value. That's a negative root 3 over 2. Negative root 3 over 2. Aha, here is my other x value where I've got root 3 over 2, positive root 3 over 2. So what are those two angles? Well, in degrees, I'm looking at 360 degrees and 330 degrees. So I might for now write that the inverse cosine, maybe I'll move this down a little, the inverse cosine of root 3 over 2 is equal to 30 degrees and 330 degrees. It's maybe also worth mentioning that it's all of these other coterminal angles. Okay, so what does that mean for my overall function if that's what my inner function is equal to? My inner function is now equal to two different things, 330 degrees and 30 degrees. Well, I'm going to rewrite now my composition function really as two separate functions because I need to take the sine of 30 degrees. I'm just going to write 30 degrees, not plus 360k. And I need to take the sine of 330 degrees. Now, the reason I didn't bother writing in those two equations 360k is because I'm looking at the sine of all of those various angles, meaning if I'm talking about any of the coterminal angles, they're going to have the same sine. So for example, this is 30 degrees right here, and I'm finding the sine of that angle. Well, that's also 360 plus 30, or 390 degrees. Well, the sine is going to be the exact same. So I only really need to consider that what I might call like the base angle, 30 degrees and 330 degrees. Okay, so what is the sine of 30 degrees? Well, wait, I have a unit circle that I'm staring at. I can determine the sine by now looking at the y value. Let's look at the y value corresponding to 30 degrees. And that would be here, let's use maybe a different color, y value. That would be a positive 1/2. Okay, what about for 330 degrees? Let's look for the y value on our unit circle right at 330 degrees. Oh, that's going to be a negative 1/2. So this actually tells me that the answer to my original question, the sine of inverse cosine of root 3 over 2, too many parentheses, didn't need that extra one, that is equal to a positive 1/2 and a negative 1/2. So I could just write that as plus or minus 1/2. If you prefer to list that as 1/2 comma negative 1/2, that's fine too. That is our answer to this question. Okay, one last example, a little word problem for us. So we've got Maya, who is wakeboarding, and she's planning on going over a ramp. The ramp is 5.5 feet tall and 12 feet long, as we kind of have labeled in our image here. We want to write an inverse trig function that will be used to find the angle of elevation up at the ramp. Then we want to actually find what the angle is. So this should feel familiar. This is very, very similar, if not identical, to the types of problems we did when we initially introduced our inverse trig. So we will use a calculator for this, in fact. Why don't we start by identifying what we're looking at? Where exactly is our angle of elevation that we're interested in? So I might just complete my triangle. I'm going to finish this triangle off here, showing that's like roughly the angle or the sort of track that our wakeboarder would go up. And our angle of elevation, that's always formed with the horizontal, and then we could say the line of sight. So we'll say that the ramp's line of sight is that red line I just drew. Meaning our angle of elevation, we'll call it theta, is here. Our horizontal is that 12 feet, and then our line of sight is that red line. So with reference to that theta, 12 feet would represent our adjacent side, and 5.5 feet, therefore, would be our opposite side. So we're able to write then a trig ratio using the opposite and the adjacent. That should tell us tangents involved here. So let's see, I'm going to write tangent of some angle is equal to, let's see, opposite 5.5 over adjacent, which is 12. Ooh, but you know what? I was supposed to write an inverse trig function, so I need to turn this into the inverse version. Meaning if I'm solving for theta, I'll say the inverse tangent of 5.5 over 12, that is equal to theta. Notice, like always when we talk about inverse functions, our input, theta, the original input, has now become my output. Whereas my output originally, this ratio, has now become the input for my trig function, or for my inverse, I should say. Now, of course, another way to write this using some vocab that we introduced today could be arctan. That's the same thing as inverse tangent. So arctan of 5.5 over 12 is also equal to theta. Those are really just stating the same exact things. And this is really where our calculator is involved. So I'm going to take out my calculator. I'm going to plug in inverse tangent. If you're using your smartphone, you probably would see ATAN to represent arctan though, so that's why that means the same thing. So I'm going to plug in 5.5 divided by 12, and what I get is 24.62356, blah, blah, blah. Let's see, I'm supposed to round to the nearest tenth, so I will just round to 0.6. My unit is, not feet, degrees. So my angle of elevation is 24.6 degrees. Okay, so that one probably doesn't feel much different than when we previously talked about inverse trig. The others, though, might feel a little bit different. Remember, the key is really utilizing that unit circle. So have a good idea of what is represented there in our unit circle. Cosine of theta is always our x-coordinate, sine of theta is always the y, and then we can sort of work backwards as we did. Okay, good luck everyone, have fun.